Hi everyone. Today, I will present my final project titled Developing Satellite AI for Regional Climate Monitoring and Policy Support. This project explores how AI can be integrated with satellite technology to monitor, predict, and support policies that mitigate the impacts of climate anxiety and climate change. Climate change is no longer a distant threat, it's here. However, its impacts differ across regions, making localized monitoring critical. By combining satellite data with AI, governments can create scalable, real-time systems that both predict risks and inform policies at regional levels. The primary objective of this project was to design an AI system capable of using satellite data to predict regional climate risks. The system should not only provide early warnings, but also generate insights that policymakers can use to create proactive mitigation measures. This project is scoped to align with administrative regions, such as counties or districts, because policy implementation usually happens at this level. The model focuses on 4 major data inputs: temperature, rainfall, pollution, and vegetation, and classifies regions by risk level. Data was simulated for this prototype, but designed to represent real satellite inputs. Pre-processing was critical. Handling missing values, normalizing scales, and exploring patterns ensured the data was usable for training an AI model. To make the model smarter, I derived temporal features such as seasonal variation, encoded region types, and scaled features so that variables like rainfall and pollution could be meaningfully compared. The random forest algorithm was chosen due to its robustness and interpretability. The dataset was split into 80% training and 20% testing. Cross-validation and tuning improved the model's ability to generalize and avoid overfitting. The model performed strongly across evaluation metrics. Using accuracy, recall, and F1 score, we confirmed reliability. A confusion matrix helped visualize performance across classes, while feature importance analysis showed temperature and rainfall as dominant predictors. Key findings indicate that regions with higher temperatures and low rainfall face elevated risks, especially when pollution is high. On the other hand, strong vegetation cover showed a mitigating effect, highlighting its role in resilience. The first recommendation is to integrate AI-driven forecasts directly into regional planning. Second, governments should expand satellite data pipelines. Finally, collaboration between meteorological, environmental, and administrative agencies is essential. Ethics play a big role in climate AI. Models must ensure fairness, avoid neglecting low-demand areas, and remain transparent. Privacy safeguards are crucial if citizen data is added. Lastly, resilience matters. Systems must default to manual backups in case of failure. This project has wider implications, strengthening global monitoring networks, helping reduce climate anxiety by providing actionable forecasts, and creating infrastructure that supports long-term resilience to climate change. A big takeaway was balancing the idealism of real-world applications with the constraints of an academic project. Designing the project modularly helped manage complexity. I also learned that AI or ML often involves trade-offs between data availability and practical feasibility. In the future, this work could be scaled up with deep learning to improve predictions. The system could also align with UN sustainability initiatives. Lastly, building user-friendly dashboards would help governments make data-driven decisions. These are the academic and scholarly sources that supported my project, ensuring credibility in both methodology and design. They informed the technical process and gave theoretical grounding for AI applications in climate change.